طيب بسم الله الرحمن الرحيم. We talked about congestion control last time, and we talked about the slow start, which is not really slow, but we start by varying or doubling the congestion window every time. And then we talked about a small refinement of this is that we distinguish between two events when there is a three duplicate ACK. A three duplicate ACK, this means that there is like some network hiccup and the network can recover from that quickly. In that case, we slow, but we don't slow like going back to one congestion window or start from scratch by having or setting the congestion window back to one MSS. Or the severe network problem when there is a timeout, which indicates like there is a more alarming congestion on the network, in which case we do have to go back and start from one MSS. So that's how it looks like, and there is a difference between, as we said before, DCP Reno and DCP Tahoe. So the basic or the baseline is that DCP Tahoe does not distinguish between the two events. So when there is any event, we either three duplicate ACKs or a timeout, then it goes back and then it goes to a specific threshold. And this threshold is can either be selected, fixed, or it can vary. And what typically happens in TCP is that TCP uses a threshold which is variable, and the variable threshold is half the congestion window size just before having the event. So if we reach to 12 and then we have an event, either three duplicate ACKs or timeout, then we set the threshold to 6. Okay, so if we have it to 18, then we set it to 9, and so on. So the threshold actually varies throughout the time. And there is like the slow start, and then there's the gradual increase after that threshold. So the threshold kind of separates the slow start period from the gradual increase of the window size. So of course in the next assignment, you will study the performance of the different congestion control techniques in TCP in a bit more details, and you will see through a simulation, and you can actually try with different parameters and things like that to measure the performance of the two techniques. So today the last topic in the transport layer is to study the fairness, and fairness is one of the very important features in networking protocols in general. Fairness talks about the fact that when there are multiple sessions competing on a specific shared link, this protocol supports some kind of fairness. So it gives resources of this link equally to all the participating connections. So fairness is a very important feature in networking in general, and it's one of the metrics that you probably measure in for any protocol, whether it's transport, network, or whatever. So basically, the way that you measure that is either analytically or through like simulation, and one of the things that we want to see here is whether, in fact, TCP with this congestion control technique provides fairness or not. And the good news is that, in a way, it does. So based on the fact that it's a relatively simple mechanism, and by changing this congestion window, when we have a packet drop or when we have a three duplicate ACK, how can we guarantee, or how can we figure out whether this technique provides fairness or not? So to do that, we conceptually try to understand what really happens inside the shared link when there is, well, the simplest scenario is that we have two links competing. So if we, or two sessions, two TCP sessions. So we have a session connection 1 and we have connection 2, and they are competing. So what we would love to have, if we have fairness, then we have the throughput or the bandwidth that each one gets is on this line, across this line. So this line is basically connection 1 equals connection 2. Okay? So this line here is connection 1 equals connection 2. So any point on this line would result in fair allocation. However, well, we can have fair allocation by having 0 on both connections, which is not good. So we want to also, approach the capacity. So this one, so this line gives us this line is actually, if we assume that for connection 1 you have x1 and connection 2 you have x2, then this line is basically connection 1 plus connection 2 equals the capacity. Okay, so this one, so this line is basically x1 equals x2. Okay, and this one is x1 plus x2 equals the capacity. So we capacity of the link, yes, which is this one. Yes. So we would love to be close to this point, basically. This is the ideal. So the ideal is that we have x1 equals x2, and it's close to the fact that x1 is C over 2 and x2 is C over 2. So we would like to be very close to this connection. So, let's try to, dig into how the congestion control mechanism can keep us close to this point as much as possible. So, well, if we start in a very arbitrary point here, where we have the slow start phase of the two connections, so this point is anywhere in this graph. Of course, obviously, this point provides no fairness, and it provides, levels or throughput which is below the capacity. Okay, so what will happen is that assuming that there is no drops or no events on both sides, then the window will start to increase in a linearly fashion, or in a way that allows the two will grow together, which means that the bandwidth or the throughput that's allocated to each one of them, it increases, and it increases in an equal way. So from this point, each of the connections will start increasing the window in the same way, right? Which will grow linearly like this, okay, until you hit a point which is above the capacity somehow. So at this point, you are above the capacity, okay? In that case, remember that if you have, well, statistically, if you have multiple connections competing on the same link, statistically, well, the probability of packet drop from each one of these connections is probably the same, okay? In which case, if, on the average, if one has an event of packet drop, probably, in the next time, the other one will have a packet drop, something like that. So that the average drop rate from both connections is probably the same. Which means that the probability of having this event on either connections is actually the same. So this scenario here talks about the fact that each of the two connections will have packet drop, or will have a timeout event, in which case we need to go back, or 3 duplicate acts or whatever, then we need to go back to half the the window size. So this point is basically half this and half that. So if you divide this by 2, you get somewhere here. Okay. If you have one, like for example, 3 duplicate acts event on one but not the other, then chances are either you will go this, you will go across this line, okay, or you will go across this line. That's if you have one event on either connections. But regardless, you will always see yourself that when you go this way, or when you go this way, or when you go this way, chances are you will reach to a point which is below the capacity. In which case, they will start increasing gradually again and in an equally fashion. Okay, so you will always increase the congestion window equally, during the gradual phase, or the after the slow start phase, and in that case you will go parallel to this line always. And then if there is an event of packet drop or 3 duplicate acts, then you will get to half the window size on both connections, and you will keep doing that. And as you can see, you always approach the x1 equals x2 line. So you will always be approaching that line, which means that you try to fill or increase the utilization of the channel in an equally manner, more or less. So even if you go beyond this line somehow, so the packet drop will always make you come closer to this line, so that you can work on this line most of the time. However, this happens through several iterations, and one of the bad things about DCP is that it's very slow in reaching the capacity of the link, and it keeps dropping below this capacity for any event, rather than just there are some techniques like the one that you have read about in the paper, in the assignment, that tries to calculate the rate based on achieving the capacity of the link, based on some optimization techniques. But then once you set the rate, you believe that this rate will achieve all these things in one shot. So you are not expected to drop drastically if there is any packet drop. In that case, you will be always in this region, but you don't really drop drastically like what DCP does.
What's guaranteed that no one increase and the other try to increase, then drop, then decrease, and the other one still increase? One can increase and the other can try to access the link, drop, and then decrease. So one will increase and one will decrease.
Yeah, chances are, again, this is based on statistical analysis, that chances are if one decreases based on packet drop, chances are when you start to increase both of them, next time the other one will have the packet drop, because on the average, regardless of the rate, the packet drop on both sides should be statistically the same. So if one drops this time, next time the other one will probably have the packet drop. In which case, the one that goes with a higher bandwidth will have to drop or have to reduce the congestion window next time.
Depending on the MAC, because for example, if we use certain schedule technique at the MAC, the one that increased maybe not dropped. If they both use Sysma, they will have this.
ليه بتدخل حاجات في بعضها كده؟ This is end to end. We don't care whatsoever about the MAC underneath. MAC is for point to point and stuff. This is application to application. ما بتدخلش الحاجات في بعضها. This is end to end.
In some cases ممكن يحصل كده one decrease, one increase.
هيحصل
اللي هو
ماشي.
يحصل equal probability ان هما الاثنين هيحصل collision والاثنين هيتكريزوا مع بعض او واحد هيتكريز، يعني قصدي ممكن in some case واحد ينكريز على طول واحد يتكريز على طول.
ازاي؟ No. Even in the Mac layer, you always have, well, if you have multiple sessions or multiple end-to-end connections or point-to-point connections, you have equal packet drop on both. If you have two streams, you have equal packet drop on both sides. If you try it on MATLAB, you will try this on MATLAB and you will see that statistically end-to-end for TCP. It's well, the statistical packet drop on both connections is the same, which means that the probability of these events is equal on both sides. Of course, if you talk about large networks, this will not be as ideal as this. So you may have some variations. It's not 100% fair. This is on a small scenario like this, but there will be some scenarios in large networks in particular that the fairness will not be as easy as this example here. In which case, the fairness will not be, you will not have like a Jane's index of 1 on all connections. This will not happen, especially in large networks. But the way that TCP uses this gradual increase of congestion window and the fact that if you have an event of packet loss or 3 duplicate acts on one connection, the other connections will have the same statistically or across a long time horizon, makes these events happen equally on all connections. In which case, you will get your fair share pretty much from the link. Fairness, of course, in UDP, we did not talk much about UDP, but UDP does not provide anything, does not provide flow control, does not provide congestion control. It doesn't have any connection establishment or anything. And we know from 455 and other courses that it's still an attractive transport layer protocol for applications like multimedia. For multimedia applications, they don't need the sophistication of TCP congestion control and flow control, in which case UDP might sound more attractive for some multimedia applications, especially the ones that have like real-time issues or they focus on real-time streaming. So in that case, TCP will become less attractive because this throttling or this dropping of the rate based on some packet drop or 3 duplicate acts is not an attractive feature for multimedia applications, because that will result into some video pauses and stuff. I'd rather forget about this packet drop. Okay, so drop it. Whatever increases beyond the capacity, just drop it. That's fine, because packet drops might not be experienced by the user that much, versus if you throttle or if you drop the rate drastically like this will result into a bad user experience right away. That's for streaming applications. So in which case, UDP will become attractive, and of course, the fact that there is no flow control makes also UDP not like a complete package. So for multimedia applications, as you were saying, we need to have control over the rate of the multimedia sessions, because we also need to have fairness in a way. So UDP does not care about fairness, does not provide any kind of fairness. So if you have multiple multimedia connections, you need to have certain level of fairness in a way. In which case, flow control will become also in a way essential, and you can use some lightweight techniques to do that differently from what TCP does in a way. So the way that TCP provides flow control mixed with reliability and retransmission and things like this is not really a good way for multimedia applications. So instead, you need to have like pretty much constant bit rate, and this constant bit rate can be calculated beforehand and then regulated across the connection. And of course, for multimedia applications, that multimedia requires a little bit of variable bit rate. So this variability in bit rate can be accommodated by a because for video and stuff, you require variable bit rate. Okay, so if we don't do any flow control or anything special, then this variable bit rate can cause some problems in the network. So instead, you can use constant bit rate and compensate for this variability using some caching or buffering at the client, which is what we call jitter. So you can mitigate this variability in bitrate by buffering the multimedia content for a few seconds, and then start playing. When you start playing and use buffering, then by the time you finish playing, the packets in the buffer, chances are packets will arrive and you can play in real time, and you can sort of regulate the traffic coming from the network and have sort of a constant bitrate on an inherently variable bitrate multimedia content. So multimedia, multimedia applications tend to use UDP with a different kind of techniques for flow control. So you do need to have flow control even for multimedia applications, but we don't need to have reliability. We don't need to have retransmissions and stuff because that's expensive. So the way they do that is by using some kind of different flow control techniques like what we call RTP, real-time protocols. So RTP on top of UDP can provide flow control, okay, without getting into retransmission, which is pretty expensive. So also for the case of fairness, remember that TCP uses parallel connections, and if you we skipped the chapter about the application layer, but for some web applications, even for transferring one web page content, sometimes you use what we call parallel TCP connections, and we talked about that briefly before. So we said that the content on the web page can be divided into objects, and each object can be transferred using a separate TCP connection. Okay, so if you have let's say you have a web content and you have a person here, graphics or video, and you have certain objects here, and you have some text and stuff. Some browsers, they use different TCP connections for each of these objects separately. So you will end up with separate TCP connections for each object, even for one web page content. Okay. So why are we talking about this? Because this will create some issues even for fairness. Okay. So fairness will become an issue here, because if you have if you have one page with one object or one unified content like text or something, or maybe you're using an FTP session transferring the content of a zip file or something like this, then you have one TCP connection for that file, and chances are all these parallel TCP connections will compete, and each one will take a. So if you have like 4, you have this one will be C over 4, C over 4, C over 4, and then C over 4. So in a way, even though overall it's fair, but this web content has got a 3/4 of the bandwidth of the channel. Okay, so because of that's why some people or in some applications they like to have multiple TCP connections, even for transferring the same content, because that tend to make you gain more bandwidth to the shared medium by having multiple TCP connections. Of course, there is a little bit of cost of establishing this connection and stuff, but in terms of running these parallel TCP connections, you will gain more bandwidth of the shared medium. So for a scenario like this, this session here is kind of jeopardized, or it doesn't take enough share of the shared medium. Whereas if this one is smart enough and it starts like 3 TCP connections, then and only then this will be fair, because the bandwidth will be divided through 6 TCP connections, 3 for each application, and each application will take like sort of a fair share of the medium. We see the issue now. So some applications, they tend to to get more bandwidth by having parallel TCP connections. And TCP does not it's not application based. So each TCP connection will take the fair share of the capacity, regardless of what application it's coming from. You see, so there is no distinction between the different applications. So,
in this case, the application will be responsible for collecting and rearranging the packet at the receiver, because there are multiple.
This is part of TCP. This is reordering and stuff. But what we were talking about here is that by starting parallel TCP connections,
we have data deviated, but on parallel TCP, each one with different delay. So who will collect the data application and rearranging this data from...
You're talking about this web... Each of these connections will run in parallel, which means that this content will go to the application, and the application, well, the TCP, and TCP will raise it to the application, and the application will... Yes, will send this. That's why actually when you sometimes try to fetch a web content, sometimes the web content itself appears progressively. You see that even the JPEG, مثلا, pictures, they start, a little bit blurred, and then they get clearer and clearer, right? So each of these objects, they get transferred through a separate connection. And the application, yes, you're correct. The application is responsible for collecting this information on the other side, and then consolidating the stream from each TCP connection, and then display it. Sometimes it displays it progressively, and sometimes it displays it, in one shot. In which case it has to wait for all connections to send the information, and then it displays it in one shot. So there is a bit of a difference. Depends on the application. Okay. So the main issue here is that if one application starts parallel TCP connections, then we have to be careful, because this application will inherently get more share of the bandwidth by doing that, which might not be a good design. Okay, so we have to watch for that. TCP itself does not handle this issue. Okay, so that's the end of the chapter. So so we talked about multiplexing and demultiplexing. We talked about reliability and flow control and congestion control, and the fact that all these mechanisms in TCP, remember that TCP does not have a separate mechanism for each one that runs separately. No, TCP runs all of these at the same time. So this is one of the inherent bad features of TCP. TCP controls the flow at the same time, provide reliability. It's sort of mingled together. So you cannot separate one from the two easily. So TCP is based on the one package, take it or leave it. So I cannot say, like, give me reliability but no flow control. Cannot do that with TCP. So you have to think differently. Okay. So we talked about the implementation on the internet regarding UDP and TCP and the different issues related to reliability and fairness and parallel connections and stuff. Of course, UDP does not have connection. So there's no connection in UDP. So all the datagrams from a specific application to a specific application, they go independently on possibly different routes, on different paths and stuff. And so reordering, flow control, congestion control is the responsibility of the application. UDP does not do any of this. So that's enough for talking about the edge network, and now it's time to get into the core network and start talking about some network layer issues and routing and so on. Okay. So so this is the end of chapter 3. In chapter 4, we talk about the network layer. So we need to switch gear and switch context to a lower layer. So now we're not talking about application to application. Remember that. This is very important. Okay, we're not talking about application to application or endpoint to endpoint communication. We're talking here about host to host. So a host is like, so it's as if one host has different applications. All these applications are hosted into one pipe. So this is host, and this is another host. Okay, so this application has many applications. This host has many applications, and now they all go through one pipe. Okay, so network layer does not care about these applications. Okay, so it talks about host to host communication. Okay, so in this chapter we need to talk about network layer services, and in network layer we have, like, again, some service models. We have the concept of forwarding versus routing, and we have the concept of broadcast and multicast and so on. We'll take a look at how the router actually works. We'll talk about even router architecture from inside, and we'll talk about different router architecture and what is the advantages and disadvantages of each one. We'll talk about some routing protocols like OSPF and RIP and EIGRP and so on. And we'll talk about how we implement all these routing protocols on the internet. So at the beginning, we talk about some introduction. So there are some important concepts that we have to talk about first before we dig into these different concepts. So at the beginning, forwarding, there is a difference between forwarding and routing. And the best way to understand the difference between the two is that, remember, like, if you are starting a new journey, if you are starting a new commute from one point to another, so at the beginning, so you might try to think about a specific path that you have to go through. This is routing. So routing is the global picture. Okay. Forwarding talks about the fact that when I get into an intersection or a roundabout, okay, where should I go in order to stay on the path that has already been planned for me? So forwarding talks about the fact that talks about the local decision by a specific router, okay, how to forward the packet. Routing talks about the end-to-end picture, okay, how the route or how the path end-to-end has been planned and how, okay. So that's the analogy here. So forwarding talks about moving packets from one router's input to appropriate router output. So a router, you can think of a router as an intersection point on the way, or a roundabout kind of a intersection. And of course, to understand or to plan for your chip end to end, you have to have some routing algorithm, some algorithms or some smart procedures that calculate this path for you. You do that, you process that using your brain if you have some idea about the city. So it's kind of, you visualize the map of the city inside your head, and then you say, okay, so I have to go this way and this way and this way. So your brain kind of, process or replaces the routing mechanism or the routing algorithm. Or sometimes you use Google Map, in which case Google Map will do that for you. Okay. So this is the difference again between routing and forwarding. So forwarding talks about the fact that in each router, magically you have some kind of a table that tells you that if you have this destination address in the packet, then you should go to output link number 3. Okay? So this is forwarding. So forwarding is a local decision that I have to take based on, in that case, based on the destination address in the packet. Okay, so that's a forwarding. Routing is the mechanism that I use to build that table. Okay, so routing has to run first, okay, to build that table. So this table will not, be built magically. It has to be built through some prior exchange of information and things like that, which is part of the routing protocol. Okay. So if you have this destination address and you send it over this link, then it's kind of, you are routing the information for this destination address in this way. So this way you can build different routing paths for different destination addresses. Okay. Okay. So that's the difference between forwarding and routing. So that's easy. One talks about local decision. The other one talks about end-to-end plan or end-to-end route. Okay. So does that mean that we have to have some kind of a virtual circuit or an end-to-end path which is already established before communication? So there is the concept of virtual circuit versus datagram, which is very much similar to what we talked about in TCP, connection-oriented and connectionless. Okay, except that again, connection-oriented and connectionless is again, remember, application to application. Here, virtual circuit is host to host, so it's like a pipe. Okay. So that's the difference. Network layer, connection and connectionless service, you have a datagram that provides network layer connectionless service, in which case, if you have packets with certain destination address, just send it. You don't have to wait for establishing the pipe or the virtual circuit before you send the packets. So the telephone network in the past used to use that concept. So before you have to make a call, first you dial. When you dial, what happens is that there is a request without sending any data. There is a request that has to go through every switch. And for each switch, the switch has to commit a certain resources for that particular telephone call. So that kind of establishes gradually the virtual circuit from one switch to another until you go to the end host on the other side, or the person whom you are trying to call. And then that person has to respond back saying that, okay, I accept the call. When you say accept or reject, then this request will go back through all the switches so that the switches will say, okay, I will allocate this bandwidth for you. So first you have to pre-allocate the resources, but you do not use it actually until you get the confirmation from the caller on the other side. Once you get the confirmation, then you say, okay, so that particular resources is allocated for this call. And that establishes the end-to-end virtual circuit. So the good thing about that, of course, is that once you establish that virtual circuit, the performance is guaranteed, because if you establish that pipe with a specific width and specific bandwidth and everything is established, then it's deterministic. Whenever you send any certain flow of packets, you know pretty much that these packets will arrive on the other side in a specific time and in a specific order, right? So you have established the pipe prior to communication, so that will simplify things and will allow you to guarantee the performance of the communication. And that was the case back when we tried to use like landlines and stuff. We need to have some guarantees over the telephone call, otherwise for audio it's going to be a big problem. So they use virtual circuit. You have to have this virtual circuit thing. Of course, again, similar to TCP, the bad thing about this is that you can establish the virtual circuit, so I can make a phone call and then I can leave the phone and not talk, in which case you are establishing the pipe and you're not using it. So you are wasting the resources of the network. Of course, the waste is going to come back to you because you will pay for that. So virtual circuit is based on the fact that the user pays always based on the time, because as long as, or once I establish this virtual circuit for you, you're going to be responsible. You pay for it, even if you don't use it. Versus datagram is more efficient in the sense of, if you don't send anything, then you don't use the resources of the network, in which case you don't have to pay anything. So that's possible if you have an application that has like variable bit rate, or it has some on and off periods of communication, in which case you will be charged only for the traffic that you send. So again, this is similar to what TCP does, except that here the service is remember that, is host to host, not application to application. So there's no choice here. So we don't have one network that provides virtual circuit and datagram both at the same time. So the network has to, all the network layer protocol has to make a choice whether this or that. So you cannot build a protocol or a network layer protocol that uses both of them at the same time. It doesn't work. So the network layer protocol has to make a choice. Has to have either datagram or, of course, so of course nowadays they are talking about like some protocols, like, or some standards like MPLS, or some protocols that work hand in hand with IP. These provide virtual circuit-like behavior on top of IP, which is inherently not virtual circuit based. So you can use some protocols on top of IP to provide some kind of quality of service guarantees over IP. But IP itself does not use virtual circuit. Okay. So this protocol, of course, is built in the core network, so the edge, we talked about different techniques for the edge. So the edge provides the traffic, and then the edge router, or the entry point to the core network is the one that uses either datagram kind of connection or virtual circuit connection.
It's the same concept like circuit switching, packet switching.
Yes, but it's the same concept. So circuit switching and packet switching is just a concept. Yeah, it's just the definition of the concept. Again, you have connection-oriented and connectionless for TCP, and it's called connection-oriented and connectionless, referring to the fact that this is application to application. So application to application is certain connection. When you take that concept down in the network layer, so this is commonly called a virtual circuit versus datagram. So virtual circuit talks about a pipe that gets established between hosts, regardless of whatever applications. So if you have virtual circuit, you can have something like UDP datagram over virtual circuit. So TCP.
But if the application is connection oriented, it must be virtual circuit.
No. There's no.
But who will guarantee the connection for the application?
Who will guarantee
And a connection.
Those are in two different layers. برضو you keep mixing layers together مش عارف ليه.
Yeah, لو layers اللي تحت guarantee connection يبقى ازاي الابلكيشن هتجارانتي end to end connection oriented. أو maybe data loss تحت ما يبقاش فيه.
Data lost, okay. I will retransmit. ايه المشكلة؟ ال connection for TCP, the connection is a state. The state is maintained by the two end applications. That's it. The network layer does not provide guarantees. Yes, of course. I don't provide guarantees, in which case I will have packet drop. Okay, so I will have packet drop, in which case I will have to retransmit from the transport layer. Okay. Again, virtual circuit here does not necessarily mean like retransmission. I didn't talk about retransmission in virtual circuit. يعني here I'm talking about virtual circuit. Virtual circuit means that I establish a pipe. Did I say that establishing a pipe means that I have to provide reliability? Those are two different issues, right? I may have to establish the virtual circuit, but I do support or I do accommodate some packet loss. That's a different story. Okay. So source to destination path behaves much like a telephone circuit. So that's what we talked about here. So network actions are analogous to the source to destination path. So in the telephone network, all the switches have to commit and have to establish these virtual circuits across all the switches all the way to the other host. And this is done through what we call cold setup. So first you have to have cold setup, and then at the end of the communication, then you have to have a tear down for each core. Okay, so cold setup, and then you start data flow between hosts, and then at the end you do the tear down connection. So that's okay. So that's easy. So each packet carries a virtual circuit identifier. Remember, this is not a destination address. There is a whole new difference between a destination address and a virtual circuit identifier. Virtual circuit identifies a specific host-to-host communication. Okay? A specific host-to-host communication. Destination address, I'm sending the address of the destination that I want to get to. But that doesn't necessarily mean I'm identifying a specific path that I have to go through. You see the difference? Here, virtual circuit identifier identifies a specific pipe ID or a specific path from one host to another, which means that this path is very well known to every single router or switch across the path. So,
But at the end, we might
No. No. Virtual circuit identifier identifies the specific host-to-host connection. Destination address is easier because destination address is already well known to the application. Okay? So if the application wants to send using datagram, it just needs to know the destination address, which is already known. If I'm communicating to an FTP server or a web server, I know the IP address. Okay? So I can just put this in the packet and send it. I don't have to wait for anything. If I use virtual circuit, then destination address will not be enough. What will happen is that the host will have to send a request. You see that? We'll have to send a request across the network. I want to establish a virtual circuit to this destination. So there is a call setup that has to happen. All the routers will have to maintain a state. So every router that this request passes through, it has to maintain a state. And then all the way to the other host. And then the other host will say, I accept. When this happens, the router will say, okay, this connection is active now, or this connection is gonna be active. Okay? And then when the source receives that acknowledgement or acceptance of the connection, then there is a virtual circuit identifier that gets assigned. This virtual circuit identifier will then be put in every single packet that goes through this virtual circuit. Okay? So this is different from a destination. Destination address, you put it in the packet, off you go. If you have virtual circuit, then I have to wait for the call setup and confirmation. And then the first router will give me a virtual circuit identifier. This virtual circuit identifier needs to be put in every single packet before I send it. Okay? So that's the difference. We'll see this using a graph. So the difference here is that each router will have to maintain a state of a specific host-to-host connection. Okay? Which is, in a way, complicates the network layer protocol significantly. Why? Because, well, if I send using the destination address and I send, that's easy. This is the datagram protocol. But for virtual circuit, each router has to remember all the combinations of host-to-host connections or host-to-host virtual circuits. All routers have to have different virtual circuit to every single host and host over the network. So you may end up with, one host tries to communicate or trying to establish a virtual circuit to all other hosts on the network. So you can imagine the number of virtual circuits that have to be established for this type of communication. So you have millions and millions of potential virtual circuits that have to be established. So the scalability of virtual circuit concept over large network like the internet is really big question mark. So there is an issue of scalability in that case. There's a big issue of scalability. So each router has to maintain a state for each connection. So, again, if you can, I can think of a specific example. If you have multiple hosts that are trying to send to a specific destination, okay? So this destination has, let's say, an address of D. So all these hosts are sending packets, and the packet will have a destination address of D, right? So if you have a router here on the path, it receives this packet. If you use datagram, the router will not have any, distinction between it doesn't know whether this is coming from this source or this source. All it knows is that if a packet comes on this port and it has a destination address of D, then send it this way. So you will have one in the router table, in the routing table, you will have one entry called D, go to port number 1. That's it. So this entry will accommodate the traffic coming from hundreds of sources. I don't care. ماشي? For virtual circuit, no, you cannot do that. صح? So first you have to establish a connection between this one and this one. And this one will have a virtual circuit 1. And this one will have a virtual circuit 2. And this one will have a virtual circuit 3. Then this router has to have three different entries. This is for virtual circuit 1, virtual circuit 2, virtual circuit 3. مفهوم الفرق? Okay, so maintaining the states for virtual circuits potentially increases the overhead of on the routers, increases the states that the router have to maintain. In addition to the fact that for each virtual circuit, I can provide certain guarantees, certain quality of service guarantees. I can have some priorities between them and so on. So that complicates the forwarding process. ماشي? So in terms of scalability, there will be an issue here, especially for the internet.
Virtual circuit complicated router task.
Right.
Don't add overhead to the packet.
No. The only overhead is the call setup. So that adds to the delay. Yeah, but once you finish the call setup, virtual circuit number is similar to a destination number as far as the overhead of the packet. We'll talk about issues related to the virtual circuit identifier now. So, but on the other side, this particular concept may be perceived in a good way in the sense that, again, I do want to distinguish between this particular virtual circuit and this particular virtual circuit. If I want to provide some service differentiation between those three connections, I cannot do that using datagrams, right? I cannot do that. صح? I cannot do that. But using virtual circuit, then I can have some priorities, some scheduling, some based on the virtual circuit identifiers in the router, in which case I can provide some service guarantees. So the good thing about virtual circuit is that you can have better control from the router point of view, but the cost is scalability. Maintaining the states is not really scalable. Okay? It was really a furious fight between virtual circuit protocols on the internet and IP. So IP is datagram, does not provide virtual circuit concept, and so on and so forth. So and there were other protocols like frame relay and ATM and other protocols that provide virtual circuit guarantees. And there were a big fight. Of course, I mean, maybe you didn't live that time when there is a big fight between ATM and IP. That was way in the past. But of course, IP was dominant, and ATM just died. And although later on, people started to talk about again quality of service guarantees from the core network. So we need quality of service guarantees. In which case, didn't we talk about virtual circuit before? So why did ATM die? I mean, we do need service guarantees. And then they started talking about, okay, so let's come up with something like MPLS on top of IP. To me, it's politics. Sometimes the solution that you come up with is not necessarily the perfect or the best solution, but you push for it and it goes. And then later on, I'll start addressing other issues as they come up and amend this standard to try to address this issue. So IP at the beginning, well, it's lightweight and scalable and stuff. Okay, so in any case, in the internet, we talk about asynchronous, we talk about autonomous system. Remember, in 455, we talked about autonomous system, right? So autonomous system is a boundary of routers that have like some regional boundaries. So if you talk, well, in any case, the internet is composed of multiple autonomous systems. So inside these autonomous systems, you can easily have virtual circuit inside the autonomous system, and it would be scalable in that case. I mean, scalability, when we talk about when we talk about internet as one unit of network, but who talks about internet as one unit of network? It does. Yeah, it's hierarchical in nature. So if we talk about hierarchical architecture of the internet, and we talk about the fact that we divide it into autonomous systems and tiers and stuff like that, inside an autonomous system, you can have a virtual circuit. Okay. And in fact, when they talked about MPLS, they talked about this same thing, that inside a specific boundary of network, you can use MPLS inside. So in any case, so the virtual circuit talks about dedicated resources. When you have dedicated resources, you can easily guarantee the performance. So that's the good thing about it. So a virtual circuit composed of path from a source to destination, specific path. A virtual circuit numbers, and okay, so someone might say, we talked about virtual circuit identifier. Why do we talk about numbers now? Okay, we'll talk about that. So one number for each link across the path. Okay, so we mentioned virtual circuit identifier. So now this is broken down into different virtual circuit ID on each link across the path. Okay, so I mean, so if that's the case, then it's one virtual circuit. Why do we need to assign virtual circuit identifier or virtual circuit number across each link in the path? So we'll talk about that. So each router will then have entries in the forwarding tables based on this virtual circuit, not based on the destination address bar, based on the virtual circuits. And as we said, this is the state of the virtual circuit, and that tends to grow exponentially with the number of connections. So that's the disadvantage of virtual circuits. So packet belonging to a specific virtual circuit carries virtual circuit number rather than destination address. So we know that. So virtual circuit number can be changed on each link. ليه بقى؟ So the idea here is that, well, the virtual circuit identifier, do you want to say something? So the virtual circuit identifier, so we have two solutions. So okay, so let's assign one virtual circuit identifier for the end-to-end connection. Well, the problem with that is that this has to be globally unique. صح? This number has to be globally unique. So on one hand, if it's globally unique, then we have to design it carefully that this number has to be very large, because we will potentially have large number of virtual circuits, right? So on one hand, this number has to be very large if we talk about one global virtual circuit identifier. So that's one problem here. The other problem is that this virtual circuit identifier has to be coordinated between all the routers, because it has to be allocated in a centralized way, right? Because if we assign it without coordination, it may happen that other two routers مثلا may assign the same virtual circuit identifier, in which case we have two virtual circuits with the same number. So that's going to be a problem. So in order to relieve or in order to relax this uniqueness assumption, so what happens in all the protocols that use virtual circuit concept is that they use virtual circuit number in a localized area. So each router, okay, will have its own interpretation for this virtual circuit number. So on one hand, this allows each router to have independent virtual circuit number for each connection, in which case the virtual circuit number can be smaller a little bit because each router will have, we don't have to have all the connection passing on the same router. Okay, it doesn't happen in a large network that all the connections pass through the same router. This is very unlikely. In which case, the router will decide on this virtual circuit number locally. Okay, but in a way, I can locally in the router I can say, okay, so I have a call setup with a specific virtual circuit number that is coming from this router, and I know that this virtual circuit maps to this virtual circuit on the output link. Okay, so the packet, when the packet comes through a router, the router has to change the virtual circuit number every time in the packet. So that's again a difference between datagrams and virtual circuit. Because in datagrams, we didn't have to change the destination address. It remains in the packet end to end. But for virtual circuit, because of the difficulty in allocating these virtual circuits in a global way, okay, because global way, it has to be coordinated across the routers and it has to be centralized. It has to be done in a centralized way, which is quite difficult. So instead, the routers decide on this virtual circuit identifier locally. And then when the packet comes, they have to change this virtual circuit identifier before they forward it. So as part of forwarding, they have to change this virtual circuit identifier every time. ماشي? In every single router. ماشي? And because chances are not all the connections end-to-end will pass through the same router, so each router will have a smaller number of virtual circuit identifiers in terms of states, and that allows this router to have shorter number in terms of virtual circuit identifier. So the virtual circuit identifier size can be relatively small in that case, rather than if we talk about global, then it has to be unique across the entire network, which means that it has to be very large.
So instead of having virtual circuit identifier, we'll have different virtual
local
numbers.
Yeah, it's like these are local virtual circuit identifiers, but for the same end-to-end virtual circuit. But each router decides on allocating the identifier locally. So it has and there is a table that says this virtual circuit on the input link corresponds to this virtual circuit on the output link. Okay? So this actually relieves us from having to coordinate this amongst all the routers. So each router will decide on the virtual circuit identifier locally. So this allows us to do it in a distributed way, which is kind of cool, right? Because we don't have to have a centralized way of allocating the virtual circuit, and it can be smaller and so on. It's a smart idea. Okay. So virtual circuit number can be changed. Actually, it must be changed every time in the packet. Okay, it must be changed on each link. Okay, so new virtual circuit number comes from the forwarding table. So in the forwarding table, as you will see here, so you have 4 columns here. So if you have an incoming interface 1, and if you have incoming virtual circuit number 12, then this goes to the output interface 3, and the new virtual circuit number that has to be updated in the packet is 22. Okay? So if you have an incoming call with a virtual circuit number of 12, this is coming from the host, so the host or the edge router assigns this virtual circuit initially, that doesn't mean that the output virtual circuit is the same. It can be different, and in that case, the router will maintain one certain state for each virtual circuit. So you can imagine the combination now between the interface and the virtual circuit number versus a destination address, and the fact that this table can potentially grow very large. Okay. So this is what we call connection state, or virtual circuit state that the router has to maintain.